Next, we want to look at what might broadly be considered as atmospheric optics. That is, some of the things that happen when light interacts with the atmosphere of the Earth. The first thing that we want to talk about is mirages. Now, unfortunately, a lot of people have a bad idea about what a mirage is because they've seen one too many Bugs Bunny cartoons. There are several variations of this, but the basic idea is Bugs is out in the desert and he's dying of thirst, and he hallucinates. And so a lot of people think that a mirage is like a hallucination that's brought on by sunstroke or something, but that's a hallucination, not a mirage. So what's a mirage? A mirage is an optical illusion, and it's caused by the process of refraction, which we talked about. Now, if you remember, we talked about how sound waves could refract through different layers of air that had different layers of density because of different temperatures. The same sort of thing can happen with light waves. And when that happens, a mirage can be the result. And so here in this image, we see the basic idea that explains how a mirage works. So normally, if the air were all the same temperature, light would go in a straight line. And so the ray of light from the tree, there'd be some rays of light that go straight across to your eye, and you would see those. But when different layers of air exist at different temperatures, the light from this tree, the ray going straight to your eye is still there, but the ray that normally would go to the ground and get absorbed by the ground, it's refracted as it passes through the different densities of the air at these different temperature levels. And so the light bends, it refracts, and it actually bends so that instead of striking the ground, it bends up and goes into your eye. Now, this picture doesn't actually show it, but there would be two beams of light coming from the tree. There would be the beam of light coming straight across that you would normally see on any given clear day. But if the conditions are just right, let's say the sun is out and the ground is being warmed up, and so the air closest to the ground is warmer than the air just above it, which is warmer than the air just above it, etc. And so the air is getting cooler as you go up, and the light is coming in, and it's going to refract through these different layers. And so you'll actually see two versions of the tree. You'll see the actual light going straight to your eye, but you'll also see this bent ray that's entering your eye too. And here's the thing. Remember, every time a ray of light enters your eye, your brain assumes that that ray of light is coming in straight, because that's usually how rays of light behave. They always go straight. But so your brain will imagine that the ray is coming in straight the way that light normally goes, and so your brain will figure out that the tree has to be here. And so you'll see the actual tree, and you'll see the light actually coming from the tree, but you'll see also kind of a ghost image of the tree coming from the light that's refracted through the air. Now here is a photograph showing an actual mirage, and so you can see the car here, but if you look where the tires touch the road, there's like an upside down image of the car too, and that's coming from the light from the car bending and then coming back up, and it goes to your eye. And so you see this ghost image of the car underneath. Now notice also you see what looks like puddles, and that's actually the light from the sky on the horizon, which normally would be coming at a downward angle and strike the ground and be absorbed, but it gets bent in the same way, so that light from the sky actually comes up and enters your eye, so you see this sort of ghost image of the sky. Now, the reason why the Bugs Bunny cartoon, Bugs Bunny always hallucinates like a full-on oasis in the desert, with palm trees and whatever else. What an actual mirage is, why it's associated with, people being led astray in the desert, is on a bright sunny day like this, when the sky is clear, the mirage makes it look like there's water on the ground in the distance. And so if you're out in the desert looking for water, if you look off to the distance, you may see what looks like a puddle of water on the ground, but it's actually a mirage. You're seeing an image of the blue from the sky being refracted and bent upwards towards your eyes. And so what happens is people will go chase after that. Go, oh, there's water over there. I'm going to go over there to get to the water. Of course, when they get there, there's no water. And so that is the basic idea of how mirages work. The next question I want to answer, and if you ever have kids, you may well be thankful that you took this course, because you'll be able to answer a question that kids ask a lot when they're little. Mommy, Daddy, why is the sky blue? Why is the sky blue? Why isn't it red or green or some other color? And the reason for that, the sky is blue because the white light that's coming from the sun, remember the sun's emitting all the different colors of the rainbow, but when that white light enters our atmosphere, it gets selectively scattered. And this is a key phrase, selectively scattered. What that means is the light gets scattered differently depending on its frequency or its color. Remember, the color of an electromagnetic wave is determined by its frequency. So same idea. It's scattering different frequencies in different amounts, or it's scattering different colors in different amounts. Now, how does this work exactly? What you have in the atmosphere, now the Earth's atmosphere is primarily made up of oxygen and nitrogen, and they make up most of the atmosphere, and actually nitrogen is by far the largest constituent of our atmosphere. Our atmosphere is about 78% nitrogen and about 21% oxygen, and then other things like carbon dioxide. To explain how this works, our book uses a great analogy with tuning forks, which we already talked about. And in fact, it calls the oxygen and nitrogen molecules in the air, they call them like optical tuning forks or light tuning forks instead of sound tuning forks. They're not literally forks made out of metal, but they behave in the same way. So let's remind ourselves about how one of the ways that tuning forks work. And so every tuning fork has its own natural characteristic frequency, its resonant frequency. And if sound waves come in at just that right frequency, it will start that tuning fork vibrating in sympathetic resonance. It will resonate with that sound wave. And so we've talked about how the incoming wave can, when it impacts this tuning fork, it sets the tuning fork in vibration. And we talked about how if this wave is at just the right frequency, you can get good sized vibrations out of it with just a little bit of energy. One thing to keep in mind is that I could have a very focused beam of sound. The beam of sound could be going in just one direction, and when it strikes that tuning fork, the tuning fork is going to ring. And then anywhere you are in the room, you're going to hear that tuning fork. It's going to send that sound out in every direction. And that process is called scattering. So the sound was coming in one direction, but then when it interacted with the tuning fork essentially absorbed and re-emitted the sound and sent it scattering. When it re-emitted the sound, it sent it out in every direction as these guys are vibrating back and forth. That's called scattering. And the same thing happens with light and the atmosphere. If this guy here is a nitrogen molecule or an oxygen molecule, you could imagine the electromagnetic wave coming in from the sun. And we know that the molecule is made out of atoms that have charges, and this thing can be set to vibrate by the electric forces in this electromagnetic wave. And if the electromagnetic wave is just the right frequency, in other words, the resonant frequency, you get pretty big vibrations, just like the tuning fork gets big vibrations if the sound wave is just the right frequency. And so what happens as these charges vibrate essentially in resonance, they send, remember, what do moving charges make? Accelerating charges create electromagnetic waves of their own. And so this guy's going to come in, it's going to excite this guy into a resonant vibration, and then that guy is going to send out light in every direction. And so we say the light is scattered. That's what we mean when we say the light is scattered. Now, what does it mean selectively scattered. All that means is that because of the size of the molecule, remember molecules are very, very tiny, right? So the higher frequency light gets scattered more than the lower frequency light. That's like if you had two bells. If you had like a tiny little bell and a really, really big bell, the tiny little bell is going to be very high pitched, very high frequency when you strike it. The really big bell is going to have a much lower frequency or be a lower pitch when you strike it. It's the same way with the molecules. The tiny little molecules, they respond better to higher frequencies. And so what that means is the higher frequencies of light, the blue and the violet, they get scattered the most. Now, if that's true, why isn't the sky violet? Actually, it is violet. But our eyes are much better at seeing the color blue than it is at seeing the color violet. So, to us, the sky actually looks more blue than violet, because even though the violet's there, our eyes just see the blue a lot better, so the sky looks blue. But that's why the sky is blue. It has to do with the size of the molecules in our atmosphere having a resonant frequency that's closer to the blue light than it is to the red light. And so the blue light gets scattered a lot more than the red light does. And so if anyone ever asks you why the sky is blue, now you can explain it to them. Now, have you ever noticed that some days the sky is a very dark blue and other days it's kind of a pale blue? It looks, almost like a mixture of blue and white. Well, that has to do because of what's in the air. When there is a lot of dust and a lot of water vapor in the air, those larger molecules scatter other colors in addition to the blue. And so what happens if you see all the colors adding together? You get white. And so normally, if you don't have a lot of dust and water vapor in the air, if the air is pretty dry, it's not very humid, and it's not very dusty, then what's scattering most of the light is just the air itself. But if you have these other things in the air that are larger molecules, they're going to scatter some of the lower frequency colors too. And when you add up all of those colors, what happens is you get white. Now, of course, the air itself is scattering a whole lot of blue. But once you start getting a few of those other colors scattered into the mix, that blue starts to look more like a whitish blue instead of a deep blue. Next, we can ask the question, why is it that sunsets are red? So you know that when you look up at the sky when the sun is setting, you see more reds and oranges and sometimes even some purples, but mostly red and maybe some orange. That's what the sky usually looks like at sunset. At least on the horizon, that's what it looks like. Why is that? And it has to do with the fact that the sunlight is traveling through different amounts of air during different parts of the day. So imagine the sun is over here. And so the sunlight's coming straight. And if you're standing right here, the sunlight passes through the very narrow band of atmosphere. And so the sunlight's not traveling through very much atmosphere at all. And so as the sunlight interacts with the atmosphere, it's being scattered. And all the blue light from the sunlight is being scattered out in every direction. And you're here down on the surface of the earth looking up. The sky looks blue because blue is being scattered in every direction. Now, when the sun is in a position in the sky so that you are basically seeing the sun setting or rising, the sunlight is traveling through a much longer path. And you can see it's bending here because of refraction. That makes it travel on an even longer path. And so what's happening is over here, the sunlight is scattering out all the blue, and once it gets to here, all the blue has been scattered out over there. So if you were on the ground right here looking up, it would seem blue to you. The sky would look blue. But if you're standing over here, all the blue's been scattered out over here, so what you see is the colors that are left over, the reds and the oranges. The next thing we want to talk about is why clouds are white. Now, It's kind of similar to what we were talking about with the water vapor and the dust in the sky, giving it sort of a washed out whitish blue look instead of a deep blue look. Well, clouds, they're not just made out of water vapor. They're actually made out of water droplets, which are much bigger. And so they're so big, in fact, they're not actually scattering the light so much as reflecting and refracting it. And so when they reflect and refract the light, all of the colors get equally bounced around. And so the light coming out of the clouds, it's basically all the colors coming out together, and it makes the clouds look white. Now at dusk, we've already talked about how the light coming in has had all the blue light scattered out. And so the light coming into the clouds at dusk doesn't have a lot of blue in it. And so what gets scattered back is the light that's still there, the reds and the oranges. And so that's why the clouds can look reddish at dusk. Now, if a cloud's really, really big, as the sunlight's passing through it, it's being scattered and reflected and refracted, but it's also getting absorbed. And if the cloud is big enough light gets absorbed that the light coming out of the cloud is dimmer, and that makes the cloud look darker. And so that's why sometimes really big storm clouds can look ominously dark. They have, they're dark gray, and that's basically what's going on with that. Now, the next topic I want to talk about is what's called dispersion. So I wanted to try to explain what dispersion is, and then we're going to look at a particular application of dispersion. Dispersion is the principle behind what makes rainbows. But first, let's talk about just what dispersion is. And so if we've already talked about refraction, and so I know that if I have a pane of glass and I have a light incident on that pane of glass, as it passes from the air into the glass, it's going to change direction. It's going to bend. And that's because of refraction. Now, when light is refracting, remember, the amount of bending depends on the change in the velocity of the wave as it passes from one material into the next material. Well, what happens is that in glass, for example, blue light and red light actually travel at different speeds. When you're in vacuum or in the air, all the colors are all traveling at the same speed. So you can have a white beam of light and it stays white and it just keeps going. But once that white beam of light enters into the prism here, for example, it refracts, and so the light bends, but because the different colors are all going slightly different speeds in the glass, they all bend slightly different amounts. And so as they continue to travel, they spread out. And so dispersion is really a change in the speed of a wave with respect to its frequency. That is, different frequencies of the wave change their velocities slightly different amounts when they go from one material into the next material. And of course, that creates different angles of bending. And so that's why when white light passes through a prism, it actually spreads out into all the colors of the rainbow. Now, speaking of rainbows, how does an actual rainbow work? That's an interesting question, right? Why are there rainbows? It occurs when there are water droplets in the sky. So usually you find rainbows when it's raining or right after it's been raining, when there's just a huge amount of just humidity in the air. Lots and lots of water droplets. Now, this picture here on the right is showing what happens to a particular ray of light as it enters into a water droplet. Now, we know that as it goes from the air into the water, it's going to bend a little bit because of refraction. And we also just learned that the colors are going to refract different amounts. They're going to bend different amounts. And so the red is going to bend a different amount than the blue. And by the way, you can see in this picture, it's always true, the blue always bends more than the red. The higher frequency light always bends more than the lower frequency light. But anyway, you can see in this picture that as the light's coming in, it's bent a little bit and the colors start to separate. Now, when the light hits the back of the drop, it actually reflects off the back of the drop. Now, you've seen your reflection on the pond before. You know that we talked about reflection off of a pane of glass. You know that even when light can go through things, some of it reflects back from those surfaces. And so that's what's happening here. The light comes into the water droplet, it starts to separate, and then it hits the back of the water droplet and it reflects. And so as it continues, it separates a little bit more, and then it comes out of the water droplet, and the red light and the violet light, they're separated by about 2 degrees. The violet light, comparing to the incoming beam of light, the violet light comes out at about a 40-degree angle, and the red light comes out at about a 42-degree angle. Incidentally, in order for you to see a rainbow, your eye has to be over here, and the sunlight has to be coming in this way. So basically, if you want to see a rainbow, you want your back to be to the sun. And generally, the sun needs to be lower in the sky. You don't want it's harder to see a rainbow when it's noon, but if the sun is, almost setting, that's when it's a lot easier to find a rainbow. But always, rainbows are going to be when the sun is behind you and the light's coming in over your head like this, so that it can separate in the raindrop and reflect off the back of the raindrop and come out towards you. Now, here's the thing that's a little bit tricky. The rainbow doesn't come from a single water droplet. It comes from many water droplets. And so here's something that you can see. Here I've got 2 water droplets here, the one on top and the one on the bottom. And the sunlight's coming in, and one beam of light hits the top drop, and one beam of light hits the bottom drop. Now, in the top drop, the light separates into all the colors, and you see the red and the violet. All the other colors would be in between, but only the red beam goes into the person's eye. If you follow the violet beam, it would hit the person's forehead or something. It would not go into their eye, and they would never see this violet color. But they actually are able to see the violet coming from the drop underneath. And so they see all the colors of the rainbow, but each color is coming from a different drop. Now, this violet guy, if the guy doesn't have a really big head, maybe that violet would go all the way past their head, and someone over here would see that violet. And so the person standing over here would see the violet from the top drop, and this person is seeing the violet from the bottom drop. This is illustrating a basic principle here. Everybody sees a different rainbow. In other words, if you're looking at a rainbow and you have a friend standing next to you and you're both looking at the rainbow together, the light that you are seeing is coming from a particular set of raindrops. The light that your friend is seeing is coming from a different particular set of raindrops. The ones that the rays of light are coming out and making just the right angles to go into their eye. So everybody sees a different rainbow, which is kind of cool. You get your own personal rainbow. And of course, if you take a step back or a step to the side or a step forward, you're seeing a rainbow that's different from the one you were just seeing. That is, the rainbow's coming from a different set of drops. Now, why is it a bow shape? I mean, I think hopefully it's pretty clear what's going on with the separation of light into colors like a prism. The reason why it's a bow shape is because we'll take the red light, for example. All the different colors come out at their own angles. The violet comes out at 40, the red comes out at 42, relative to that incoming beam of sunlight. So this is, let's say, take the red, it's coming in at 42 degrees. Every part of red that you see that's coming to your eye is coming in at a 42-degree angle. Imagine you have this triangle here, and this angle is set at a 42-degree angle. And so when you're looking up, you see the red light coming from the rainbow right here. Now, if you were to rotate this, because this dashed line here represents a 42-degree angle to the eye. So everywhere on this arc, the straight line into the eye is at a 42-degree angle relative to this flat part. So that's why you get this sort of a bow effect, because that is the part of space where light coming from that part of space, in other words, light coming from raindrops on this arc, those are the raindrops where the red light will be at the right angle to go into your eye. And so everywhere on this dashed line, you would be able to see red. If you were at a slightly different angle, you would see a slightly different color. And if you see all of the colors, you're seeing the entire rainbow. Now, what's interesting, it's not actually a bow, it's a circle. The reason it looks like a bow, though, is because it gets interrupted by the horizon, by the ground. Let's look at another picture, and hopefully this will all make sense. So this is the sort of the complete setup for what a rainbow looks like. Now, what you have is you have a region where there's lots of water droplets, either because it's raining or maybe it just rained. There's a lot of water droplets in the air. The sun is behind you, and it's, coming in, the sunlight's coming in relatively parallel to the ground. And when the sunlight gets to all these water droplets, it refracts and reflects in those water droplets like we talked about, so that the light comes out backwards and shoots out towards your eye. And at 40 degrees, you see the violet light, and at 42 degrees, you see the red light, and at the other angles in between those, you see the other colors of the rainbow. And as we were talking about, we could sweep that triangle back and forth, and you see that you make an arc. Now, that arc is part of a continuation of a circle. You could actually see not rainbows, but rain circles. If you're on a plane flying in the air, you could actually see the whole circle because there's no ground to stop it. You can see right here where those rainbows, they're turned into dashed lines. That's because right there, that's where the rainbow is intersecting the ground. And of course, it's not literally touching the ground there. It's just, the light coming in from those angles. That's what it looks like. Now, sometimes you can actually see a double rainbow, and I hope you guys can see this in the picture. You can see the main rainbow here, which is brighter, but there's also right here, you can sort of see a secondary rainbow. You can see sort of the red here and the yellow and the green. And the reason for that is if the sunlight's coming in at a somewhat higher angle, as you can see in this picture here, what you can actually get is a double reflection. And so you get the sunlight enters into the raindrop, and then it starts to separate into the different colors. That's, again, dispersion. And then it reflects once from the back end of the raindrop, and it goes upwards, and it reflects again from the top back end of the raindrop, and then it comes out. And so when the sun is at just the right position, you can get these double reflections inside the drops. And so the rays of light come out at different angles. And so that's what creates that second rainbow. And I don't know if I actually said this or not, I don't remember, but this phenomenon is actually sometimes called double rainbow. So, if you ever see a double rainbow, that's what's going on.